That's a good question. I mean, I suspect I probably do it without realizing quite often that a lot of the things that you study in maths are kind of underlying structures underneath things like looking at permutations, like ways to reorder stuff. And just occasionally you'll approach a problem in the real world and you think, oh, there's a bit of maths I can use for this. This is good. I remember very strongly, we bought a wardrobe from IKEA. So it was a flat pack thing that we had to assemble ourselves. And it had a little note in with it. And it said, if your room is taller than this height, you can build the wardrobe lying down and then stand it up. But if your room is shorter than this height, you're going to have to build it standing up against the wall. And we thought, that's really weird. Why does it say that? And then we just realized it was trigonometry, that literally the wardrobe wouldn't be able to move past that. If the room wasn't small enough, you wouldn't be able to stand it up, because when it's on an angle, it's going to be physically taller than it is when it's flat. And we're like, should we just check that number is right? And we did the calculations. We're like, yeah, that's pretty much the right number. That's good. And obviously you could just test it by physically putting the thing in place. But, you know, it's sort of, you have those sort of exciting moments of like, oh, I'm doing a thing and it is useful. But it is a lot of the sort, especially the more abstract stuff, because obviously that's a very concrete calculation example. That's the kind of thing that people think of as maths. But even the sort of more abstract sort of looking at structures behind things, it is all kind of in there underlying it. And I guess I don't necessarily consciously do that. I think there's also an extent to which I know the limitations of mathematical models. And this is another thing that it's important to understand as a mathematician who interacts with the real world. And in my research and in the kind of maths that I love to study, I'm mainly a pure mathematician. So I'm basically just thinking about these really abstract, nice ideas. But I'm aware that applied mathematics is this notion of saying, okay, here's a real world situation. How can I model this? And in order to model it, I will need to simplify this situation and just reduce it to sort of a number of small variables that I can then, you know, change the values of and see what happens. But actually, in doing that, you lose quite a lot. And there's sometimes where you see a situation and you think, can I use maths? It's actually not going to be worth it, because, you know, the amount of effort it would be to put the mathematical calculations together. I might as well just try the different things that I could do here and see which one works. You know, I could sit down and work out all the possibilities and decide which one is best, but actually that will take longer. So you kind of weigh up when it's actually going to be useful. But the fact that you understand the structure and you know that all of the possibilities are out there is quite a nice thing. And kind of when maths interacts with the real world in that way, it is really satisfying. Like the nice example is one of my colleagues who does maths talks about the maths of juggling. So he's a juggler and he has a lot of skill in being able to juggle things. And he was, back in the day, he was involved with some people who developed a notation for writing down juggling tricks. So, you know, you're throwing the balls in the air in different ways, but there are actually some patterns in that. And there are some very sort of easily written down different juggling tricks that you can do. And they started writing these things down. They came up with a notation called sight swap. And what they found was that actually, you know, there's this one that you do 3 and 3 and 3, and you can just juggle 3 balls, or you can do, 3 and 5, and you can juggle 3 balls, but in a different pattern. And there was one in between that was like, there was a 4. And they were like, is that a thing? Has anyone done that? Is that a juggling trick? And they realized that it was a possible juggling trick that you could do, but no one had ever done it before, because no one had tried to write it down in this kind of way. And they did it, and they were like, this is a thing. And it became like the new craze for several months. It was like the hot new trick in juggling that no one had done it before. But it was sort of sat there in between these 2 other tricks, just waiting for someone to find it. And it was only the mathematical approach that had kind of revealed that. And I think that's a really nice example of the fact that sometimes just trying to sort of encode something in a more rigorous mathematical way will help you to understand it better, even if all you're doing is throwing balls around in the air. You know, it's not anything important or serious, but it is actually, there is a structure to it and there is a pattern behind it.